legs and hands? I do not like them, Sam. I am.
Would you like them in a house? Would you like them with a mouse? Still a little bit.
I do not like them in a house. I do not like them with a mouse. I do not like them here or there. I do not like them anywhere. I do not like 3 days in hell. I do not like them, Sam. I am. I tell them my students have all the fun. You may have noticed that the effect with the helium doesn't last very long. Because helium is less dense than air, it wants to float up out of your lungs, and the effect doesn't last very long. But the effect of the sulfur hexafluoride lasts a long time. The sulfur hexafluoride is much more dense than air, and it wants to stay down in your lungs. Now, the other thing to remember is that these gases are not poisonous, so they're safe to breathe from that perspective, but there's no oxygen in them, so we get a little lightheaded doing this demonstration. We've been talking about sound. We know that sound is caused by something vibrating, even our vocal cords vibrating. That sound is a wave. We talked about noise-canceling headphones. This is a cell phone. Kids, I am told that there are cell phone ringtones that you can download, that you can hear, but your parents can't. They are banking on the fact that your parents have lost the ability to hear high frequency. See, kids? You never know when your knowledge of physics will come in handy. So please, take good care of your hearing. It never gets better, it always gets worse. Please take good care of your hearing. The physics of sound. Our next topic is temperature. We're going to talk a little bit about temperature. Temperature tells us how fast the atoms and molecules that make up a substance are moving. Everything is made up of atoms and molecules. The chairs you're sitting in, the clothes you're wearing, even you and I are made up of atoms and molecules. And atoms are tiny, tiny little things. If we could stack atoms on top of each other, 5, 50, 500, 5,000, 500,000, 500,000 atoms, if we could stack them on top of each other, would be the thickness of a sheet of paper. Okay? They are tiny, tiny little things. Now, they're always wiggling. They're always vibrating. Not unlike some of you sitting in your seats right now. And temperature tells us how much they're wiggling, how much they're vibrating. The hotter something is, the more the atoms and molecules are vibrating. And the cooler it is, the less they're vibrating. So this analogy kind of helps me sum things up for you. Sometimes you're out on the playground and you just are standing still talking to a friend, right? And sometimes you're running around chasing each other, playing tag. Who has more energy? It's the same with physics students. Who has more energy, the kids running around or the kids standing still? The kids running around. Who gets hotter? The kids running around. Who takes up more space on the playground? The kids running around. It's the same with atoms and molecules. Thank you. It's the same with physics students. And it's the same with atoms and molecules. Right? As you heat them up, they wiggle more. They need more elbow room. They take up more space. It's like this. If we took you kids and put you on a dance floor, and the music was low, and you're just kind of dancing softly, quietly, we could fit you all on the dance floor. But we crank up the music and you start jumping and swinging your arms, what happens? We need a bigger dance floor, don't we? Yeah, it's the same with atoms and molecules. Almost universally, there's always an exception, isn't there? But almost universally, solids, liquids, gases expand when you heat them up and contract when you cool them down. Now, Kimmy is going to show us what happens to a solid metal wire when we heat it up.
Make sure we're all set up here. Alrighty. Now, who here has ever looked safely inside of a toaster while it's on? Okay, now hopefully you've noticed those kind of glowing red lines that wrap around the inside. Yeah, okay, great. Well, those are actually metal wires that we run electricity through to heat the wires up, and in the process, they expand and they also heat up your bread to make toast. So here we have a nice large-scale demonstration of this. We have a wire connected to both sides of this board and hooked up to electricity over here. So far, no electricity is on. And this wire is a nice room temperature. And I want you to notice these white markers along the backboard of this, and then also the white pieces of paper hanging on the wire. Those are there to show you the initial position of the wire while it's at room temperature. Now I want you to pay attention to what happens as I turn the electricity on. Okay, so pretty quickly, you start to see that wire droop like that, right? Which means it's clearly expanding. But how do we know that it's expanding because it's hot? Should I touch it? No, we never touch something, one, we think is hot, and two, an open wire hooked up to electricity. But we could try turning up the electricity a little and see what happens to our paper. Should I do it? Okay. Turn it off. You're right, we don't want any fires over here. But hopefully you all can see it start to smoke on the screen, and those of you up front can probably smell it. So that's obviously a hot wire. Now that I've turned the electricity off though, I want you to notice how the wire is coming back up to its original position. And that is thermal expansion of a wire.
That wire is a solid metal object. We have other solid metal objects in the Bay Area, right? Bridges. I am told the Golden Gate Bridge is about 1 meter longer in the summertime than it is in the wintertime. What's a meter? About that much, right? 1 meter longer in the summertime than in the wintertime. And the women and men that design bridges have to build these expansion joints into the bridge, so the bridge can expand and contract, and it remains safe, and we can drive over it. Now, I'm not going to do a liquid for you. You all probably have seen a thermometer, probably with that red liquid in the bottom, and maybe it's hanging on the wall in your classroom or at home. The room heats up, the liquid heats up, the atoms and molecules wiggle more, they need more elbow room, they push higher up, and we read a higher temperature, right? It works because of thermal expansion. Now, we're going to do the gas for you, like the air in this room. I'm going to fill up some balloons, and we're going to use liquid nitrogen to make them cold, and then we'll warm them back up to room temperature. I'll tell you more about liquid nitrogen in a minute, But for now, all you have to know is that it is really, really, really cold. Okay, I've got some balloons here. Are they going to fit in my bucket? Looks like those fit. I've got some more balloons here. Are they going to fit? I've got some more balloons here. Are they going to fit? What must be happening to the balloons for all of them to fit? They must be shrinking. They must be getting smaller. Now, they're super cold. We're going to take them out and let them warm up. And we'll see what happens when they warm up. Oh, they're stuck together. That's okay. Thermal expansion of a gas. Now, there's something else I think of when things get really cold. Here I have a bouncy rubber ball. Oops. Bouncy rubber ball. And we're going to make it really cold. Maybe you've done this experiment at home. I don't know what to. Have you done this with a piece of bread? You put bread in the freezer, and when it comes out, it's very hard and brittle, right? That's because when you cool something down, the atoms and molecules don't wiggle as much, and when they're not wiggling as much, they can hold on to each other in a more rigid way. Let me tell you a little bit about this stuff. This is liquid nitrogen. The air in this room that we're breathing is mostly nitrogen. It's about 80% nitrogen, about 20% oxygen. And of course, there's some moisture, there's some water vapor in the air too. Now, if I start with a solid object, it's solid, it's hard, because the atoms and molecules are holding on to each other in a very rigid way. They're still wiggling, they're still vibrating, but they're holding on to each other in a rigid way. We add some energy and heat it up, and the atoms and molecules vibrate more, but they're still holding on to each other in that rigid way. We heat it up some more, and they vibrate more. And pretty soon, they're vibrating so much they can't hold on to each other in that rigid way. They kind of break free from each other, but they have a long, loose way of holding on to each other. That's a liquid. And you keep heating it up, you keep adding energy, and they vibrate more and more. And pretty soon, they're vibrating so much they break free from each other, and they can't hold on to each other at all. They are independent of one another. That's a gas, like the air in this room. So, the water molecules in this room are going by each other so fast they can't grab onto each other. But what's happening around the bucket here? We're making this little cloud. That's because it's very cold around the bucket. So cold means slow. The atoms and molecules get cold around the bucket, they slow down, and they get slow enough they can grab onto each other and form these little droplets. We call that condensation. Okay, so sometimes on a summer day, a hot summer day, you get a nice cold glass of ice water, and what happens on the outside of the glass? It gets wet, right? That's the moisture in the air condensing on the glass. Now, I need to tell you how cold this is, right? The air in this room is about 20 degrees Celsius. Water freezes at 0 degrees Celsius, and this is about negative 200 degrees Celsius. It is really, really, really cold. So let's see what happens to our racquetball. I have to put on a thick protective glove because when you touch something that's really cold, it's like touching something that's really hot. It'll damage your skin, it'll burn your skin. So it shattered, didn't it? Now if we wait a little bit, these pieces, they're going to warm back up, and they're going to be soft and rubbery again, but they're not going to be a ball again, are they? All right, I think we're done with this now, right? Am I forgetting something? There's a banana in there. What should we do with that banana? Let's see, bananas are usually really soft, right? This one is going to be frozen solid. Can you think of some kind of a tool that's really hard? What? A hammer, yes. Okay, so we'll get our nail out. And I'll put my gloves back on. Well, I got a few good hits on that one. Eventually, it shattered. Now, I could wait. If I waited long enough, this banana would warm back up, and I could eat it if I wanted to. I probably won't want to. This is one of those demonstrations it's best to clean up while it's still frozen. Now, the other thing I think about when I'm thinking about temperature is how does heat move? How does heat move through a substance? If I had a metal rod in front of me, and the whole rod was the same temperature, all the atoms and molecules would be vibrating about the same amount. If I hold a match under one end and add some energy,